This one is not that bad. The problem itself is not that difficult. It's just long. I'm not going to read the whole thing. In essence, we have a jar of tea at some initial temperature. We add some ice, and of course, there's a heat exchange, and the drink is colder. We learned that we're not really cooling down the jar, although we say it like that. What's happening is there'll be an energy transfer from the tea to the ice, so you are increasing the temperature of the ice. And what we want to know is how much of that ice is left. That's what we want to know. Let's write down what we know. Okay, there we have it. So I decided to use 1 for the tea and 2 for the ice. We need the latent heat of fusion for this problem because we're going to melt ice. Now, what in the world is M3 and F sub M? Because this problem can get messy, what I decided to do is M3 is what I'm looking for. So that's going to be what's left of the ice. And M2, sorry, not M2. M2 is the original amount of ice. M sub M is the melted ice. I know I could say water, but I'm going to consider the tea to be water. So now we know. M3 is what I'm looking for, is my answer. And M sub M is the melted ice. All right. Let's see what's happening with the physics. So the ice is going to melt. Why? Because it'll be in contact with the tea, and that tea will transfer energy away into the ice. So we can say that Q1, which is for the tea, is the energy required to first melt the ice and change the temperature of melted ice. Okay, now let's come up with an equation to represent what we just said. Q1 is simple. Melt ice, so we know that's mass of the melted ice times the latent heat of fusion. And then this one, change temperature. Well, we know that you have a change in temperature by means of energy exchange. So is that Q equals mc delta T. But of course we'll have melted ice, that's water, so we can say C1 and then delta temperature 2, because the ice is what's changing. Well, not the ice, but when the ice melts, then that melted ice changes its temperature. All right, because we need melted ice to find what's left of the ice, let's solve for it, which means we have to factor it out. Okay, let's divide by my expression inside the parentheses. We know these two are going to cancel. I'll write my unknown to the left. Okay. Now, the only thing we have to do is set up our change in temperature. Don't forget we want a positive number. So I'll just continue to the right. Delta T1, that's the T. The initial state of the T, the initial temperature of the T, T1, is the highest that it'll get because that's how the temperature of the system started. So it has to be higher than the final temperature of the mixture, of the iced tea, if you will. So there we have it. For delta T2, well, T2, that's the initial temperature of the ice, 0 degrees. So then we can say that the change in temperature would be the final temperature of the iced tea minus the temperature of the ice, which is T2. because T2 is 0 degrees Celsius, I can just ignore it. So I just wanted to show you why I'm going to get rid of, oh, I'm just going to write it again. That way you guys know what I'm doing. Okay, so now how do we find the remaining ice? Well, that's simple. We said it was the original amount of ice minus melted ice before we plug in our numbers. Some of you might have said, why didn't you convert from grams to kilograms? That's a valid question. The reason why is when I plug in my numbers, you'll see that my units for specific heat and latent heat of fusion will cancel, which means I'm going to be left with grams. And that's what I want because the question wants me to give my answer in grams. So because of these two and how they're going to cancel the units, I do not have to convert these into kilograms. Just so you know. Let me plug in my numbers. Let's see what I get. So very carefully I plugged in my numbers. I saw that the melted ice was 10.8 or 10.797 grams. So I subtracted that from 95, as you can see. So I have 84.202, let's round to 2.03 grams. And that's my answer.